Hi. It is the second part of section 2.5 continuity. We'll consider here some properties of continuous functions. First one is about compositions of functions. Let's the theorem. If f is continuous at a point A and g is continuous at f of a, then their composition is continuous at point A. I'll try to explain the theorem a little more detail with solving this problem. This given function can be written in this way. F of x is now here x minus 2 over x squared minus 2. And g of x is now absolute value of x. Then the given function can be written in this way. Y equal here g of f of x. So for this f of x and g of x is absolute value, so that eventually this given function is same as that. Now the function is saying that once it is continuous at a point A, then now this function is continuous. Even though it has cursor in its graph, it is continuous. So that as far as f is continuous, then eventually their composition must be continuous. Now this is continuous on its natural domain. So natural domain is now x squared minus 2 is non-zero, which is the same as x squared is not the same as plus minus square root of 2. That is natural domain. And we already know that the rational function is continuous on their natural domains. So it is continuous in its natural domain. And now this is continuous function. So their composition must be continuous. So we prove that this function is continuous on its natural domain. Okay, same way, we can show this is now continuous on its natural domain. Okay, let's try to write down this one as a composition. Okay, f of x is the same as sine squared x over x squared plus 2. And g of x is here now, that is square root of x or x power half. Now this one is, because it's non-negative and this is always positive, so that is larger than equal to 0. And so that range of f is now naturally the domain of this g of x. So here, this one is always continuous. So natural domain is now domain for f is same as whole real line. And now also the range is now non-negative, so that for every point is well defined. So overall, this domain is whole the real line. And this is continuous, and also this one is continuous, so that eventually here the y equal g of f of x is continuous everywhere that is over now the whole domain. Okay. Okay, that's the conclusion. Okay, now we have another theorem. Limit x approaches a, f of x equal b, and G continuous in B, then here we have, okay, limit and G of fx is just now same as G limit f of x, and now we already assumed here that same as B, so that it can be replaced by B. Okay, in this mathematical statement, now the main thing is that once that is continuous, if G is continuous, okay, then now here limit and continuous function here applied the other way. In this case, G is applied first, but in this case, limit applied first. That means that limit and continuity are commutative. You can change when, so that the limit should exist, so that we assumed in the beginning limit exists, so that you can change continuous function and limit. The applications can be changed. Let's see this example. Here, continuous function and over there limit exists, so that the given term is the same as now cosine, and first we are applying limit, so that there is a limit. Here x approaches pi over 2. And here the terms are 2x plus sine and 3 pi over 2 plus x, like that. So cosine, which is continuous function, and limit, commutative. So we apply limit first. But you can do this one when the limit exists. Okay. Now here we are considering inside this parenthesis, then that one, for that one now is approaching to, okay, twice of pi over 2 is same as pi, and then now there is a sine here, 3 pi over 2 plus pi over 2. And of course here again, this limit is applied for this term. Now you can apply the limit part by part. That is basic property of the limit. And again, that limit is appearing in front of this sine. Now sine function is also continuous, so that you can apply limit first, so that limit first, so we reach at that one. So here is same as pi plus sine, now 2 pi, which is 0, so that we reach at pi. So it's the same as now cosine, same as now in the limit, it's the same as cosine pi, which is minus 1. So that is the final answer. So once it is continuous, and then you can change limit and continuous function, but the limit should exist. Okay, now second part of that in this video club is about intermediate value theorem. Okay, let's read the theorem. Suppose that f is continuous on the closed interval, and let n be any number between fa and fb, and here we assume f of a is not the same as f of b. Then there exists a number c between a and b such that fc is n. If you read this mathematical statement, then it's not easy to understand. But let's consider these figures, then you can understand quite easily. Okay. Now, first condition is that f is continuous, defined on a closed interval. a to b. So that is now the condition. Is continuous function defined on closed interval. And the secondly, here we have fa is not the same as fb. Then we can choose, okay, and if we choose any number n between f of a and f of b, f of b and f of a is in horizontal directional quantity, I mean the vertical directional quantity. If we are choosing any number n between f of a and f of b, so n is also a vertical component number. If we choose any n, then now we can find the c between a and b. Over there c, so c is now horizontal the directional the quantities. So there is a c such that at c the function value is n. It must be true because it is continuous function. So the function is defined from here to there. The continuous function means that it is connected. And earlier we start with the continuity. Once there is no break, then we'll say the function is continuous. So the continuous function means from here to there, it is connected. So if you are making any the horizontal line start from that position n, then the horizontal line should meet the curve. And in this case now we meet here. So if you go down vertically, then there will be c. So at c the value must be n. If you are choosing n a bit lower, different way, like in this right side, then now if you are making horizontal line, then there are 3 points, C1, C2, C3. But anyway, if you go down vertically, then here, and so that it is C1, C2, C3, but for each point, C1, C2, C3, the height must be n. The theorem is saying exactly this, the situations. Because from the point A, then f of a, and b, then f of b, is connected. Continuity means is connected, and by using a curve, it is connected. So that if you are making a horizontal line, then this horizontal line should meet the curve at least 1 point. So the existence, their existence or number means that there is at least 1 point, one number c, such that f of c equal n. Okay. Now, consequence of the intermediate value theorem is here. So continuous function is connected. Basically, once it's connected and there's no breaks, then it is continuous function. And here, the intermediate value theorem can be used to just prove that some existence of the zeros of a function or roots of equation. Okay, if you try to find x satisfying f of x equals 0, then the x is now root of the equation. Or you may say that the x is now 0 of the function. And so by using intermediate value theorem, we can prove that existence of a solution in a given interval. And based on that, you may start searching the solution. If there's no solution, then basically useless search. So from the beginning, you may make sure that there is a solution in a certain interval. Okay, let's try to solve problems here. Use the intermediate value theorem to show that there is a root of a given equation in the specified interval. Okay, let's try to solve this problem first. Okay, the function is now continuous and defined on a closed interval. So let's start with, for example, f1, then is 1, then 1 plus 1 minus 4 minus 4, so that there's a minus x. Now how about f3? And so it's the end point, and 1, f1, and f3, we are checking the value. 3, then there's 27 plus 9 minus 12 minus 4. So that, okay, that whole thing is 20. Here, pictorially, we don't know the detail. However, now pictorial is given in this way. At 1, okay, at 3, so x is 1, now x is 3. X is 1, the value, the function value is now minus x. That is a minus x. And at 3, the function value is now 20. So that is 20. So here, that's the point. And between 1 and 3, we don't know how many times, in fact, it's the maximum 3 times. But anyway, we don't know how it is given. But anyway, if you try to connect it from this point to that one, then anyway, it is hitting x-axis. Oh, sorry, you know. And it should hit x-axis like that. So there's x-axis. So there must be some point C such that now in y direction the value is 0, so that this C should exist such that f of C equal 0, because it is connected from negative to positive. Somewhere the value must be 0. The somewhere is now C. Okay. And so we can prove in this way there is a root of the given function in the specified interval. Okay. This one is not a form of fx equals something. So you can change this one into the form. Okay, we define fx equal here e to the x. We move this one to left hand side, and minus 3 plus 2x. Okay, now f0, which is same as e to the 0 minus 3 and now plus 0. So that is 1 minus 3, so it's a minus 2. How about f1? f1 is e to the 1 minus 3, and if x is now here, okay, if x, just a moment, x is 1, okay, e to the 1 minus 3 and plus 2, which is same as now there's minus 1, so e minus 1. E is larger than 2, so it is positive. In the beginning, the value is negative, but later on, the value is positive, so that there must be some C between, and now, okay, you don't have to write down this closed interval between 0 and 1, such that at C, the function value must be 0. So existence of a root is guaranteed. by using the intermediate value theorem. Intermediate value theorem is true for only continuous function defined on closed interval. Okay, so if it is not continuous, then you cannot apply the theorem. It's working for only continuous function. Okay, here, and final subject in the second part is this one. We have to define function value at a point such that here this one is continuous. Right now, once x is 4, then the denominator becomes 0, so that it's not defined. So we here will expand the function and we'll try to define f over 4 such that at 4 the given function is now the continuous after extension. Okay, here. Now, in order to do that, basically limit x approaches 4, fx must be same as f over 4. So after finding this value, once it exists, then the value must be assigned for f over 4. Right? So let's try to find this one. Now limit of fx is same as now limit here x squared minus 16 divided by x squared minus 3x minus 4. Okay. Once x is approaching 4, then the denominator is 0 and also numerator is 0. So that here we have, now that should have x minus 4 as a factor. Then the remainder part must be x plus 1. Okay, the top one is now x minus 4, and here x plus 4. X approaching 4 means x is not 4, so that we can cancel out these two. So it is the same as now limit, okay, x plus 4 over x plus 1. X is approaching 4, so there is 8 over 5. So if you define f over 4 same as the value, then eventually this equality will be satisfied. So here our answer for the problem is f at 4 must be here 8 over 5. That's the final answer for the problem. Okay, this is the end of the section. Now we'll try to solve one problem. Okay, last one, and show that the absolute value function is continuous everywhere. Okay, part A, and pictorially, and here now that is given in this way, and y call x absolute value, so it is continuous. And of course that one is same as here x, when x is larger than or equal to 0, and now minus x, here x is negative. So you can start with that, and either side they are continuous, and of course this one is now right continuous. And also if you are checking left limit as x approaches 0, then again it is approaching 0. So that here at this point it is continuous and every else continuous, so that it is continuous function. Now part B, prove that f is continuous on interval, then so is f absolute value. That means that here, okay, start with this assumption. We assume this one, and we want to prove that absolute value of f is continuous. So assumption and f is continuous on an interval that is same as limit x approaches to a and f of x is now same as f of a for every choice, for any choice of a inside the interval. Let's say that is on interval I. Then in definition, it is the same as that one. So for every point is continuous, then it is continuous on the interval. Okay, that is assumption. And from there on, we want to show that here what you need is basically under the assumption here limit, okay, x approaches a absolute value of fx is the same as absolute value of f of a for any choice of a inside of the interval. That's what you need. Okay. Now, but here we already assumed this one, so that, and now, okay, and we start with this left hand side and limit x approaches a absolute value of fx, that on. Now earlier in theorem, okay, let's go back here. That is, okay, this one. And limit and continuous function commute. Yes, they are commutative, so that, and in application, and g can be applied first, or limit can be applied first when the limit exists. Okay, so that's the theorem we can use for solving this problem. Okay, here, now the reason we prove in part A that the absolute value function is continuous is that, okay, this absolute value function is continuous, so we can change the application. So that means here absolute value and limit can go inside and f of x, and like that. Once the limit exists, then we can do that. But already we assumed that the limit exists and the same as f of a. So that is assumption. If f is continuous function on interval, that is assumption. Okay. So here we know that from assumption that's same as f of a. So that is now absolute value, and inside will be f of a. So we prove that. That is, now, of course, for every choice of a inside interval, it is true. So absolute value of f is continuous. You should understand this mathematical argument quite nicely, right? Okay. But here, I'll say again, this is assumption, and under the assumption, we have to prove that, okay, this assumption can be written in this way. Okay, that is assumption basically. And what you need is that one. So by using assumption and by using the factor that absolute value function is continuous, we can prove that required one. So we finished part 2, part B. Okay, so you can do remainder part yourself. Thank you.